This paper describes a technique for single-shot full surround 3D scan of an object using a single camera and a kaleidoscope with a neural surface representation. Our goal is to generate digital replicas of real-world objects, which is critical for many applications such as augmented reality, virtual reality, and 3D printing. There are several ways to achieve the full surround 3D reconstruction, such as using a turntable, moving a single camera, or building a multi-camera system. However, using a turntable or moving a camera cannot handle dynamic objects. Also, multi-camera system is hard to build because of its cost and complexity. A simple way to achieve the full surround coverage is using a kaleidoscopic imaging, which consists of a single camera and a multiple planar mirrors surrounding the object. It allows us the full surround coverage by providing hundreds of different viewpoints from a single image. If we can decompose the image into multi-view images by identifying which pixel corresponds to which virtual camera, which is called the labeling problem, this can be considered as a virtual multi-view images. Then we can solve the 3D reconstruction problem using multi-view stereo as if we have multi-view images. However, it is challenging to solve the labeling problem because the label itself is a function of the unknown object shape. In other words, we need the label to solve multi-view stereo and obtain the 3D shape, but we need the 3D shape to solve the labeling problem, which is a chicken and egg problem. To avoid this problem, a previous method used only background pixels, where the label is independent of the object. By carving out the space that the reflected background rays are passing through, it could achieve an approximate 3D shape of visual hull. The label is also obtained by simply running ray tracing to the visual hull in the kaleidoscope. However, since the foreground pixels and textures are not used in the visual hull, it cannot capture high-frequency details on the surface, such as the face of the bust, and cannot handle the shape with complex visibility, such as the chair. To solve this problem, we propose a neural kaleidoscopic space sculpting method that sculpts neural surface to make a silhouette-consistent and photo-consistent shape. It avoids the need to explicitly estimate labels by carefully using the silhouette and texture information to carve and model the space. It is based on two observations from the definitions of background pixels and foreground pixels. First, background rays do not intersect with the object for all bounces. Therefore, we can update the 3D shape by carving the points on the background rays, as they will never intersect with the object. The second observation is that the foreground rays intersect with the object for at least one bounce. From this observation, we can update the 3D shape by modeling a point on the foreground rays, as there will be at least one intersection with the object. The foreground intersection points also can be used for texture information. We use a neural sign distance function to facilitate the update of the 3D shape. Please refer to our paper for more detail about how to select the points on the rays. In summary, we introduced a technique for the single-shot full surround 3D reconstruction that can be used for 3D printing and virtual reality. This is achieved by our neural kaleidoscopic space sculpting method that jointly solves the labeling problem and 3D reconstruction problem. We also analyzed the information encoded in a kaleidoscopic image and show that a single pixel in a kaleidoscopic image is equivalent to multiple pixels in each multi-camera counterpart, not only for background pixels, but also for foreground pixels. Please refer to our paper for more detail. Thank you.